with our afternoon session with a talk by Iva Halacheva, who's going to tell us about w-tangles and topological interpretation of Kashiwara-Vergne group. Iva?
Thank you very much for the introduction and for the invitation. I'm sorry I couldn't be there in person, but I hope to meet all of you at some other point in the future in person. So, so my talk will be a mixture of some objects in topology and seeing how they can be considered from an algebraic point of view and reveal some interesting ideas in Lie theory. And I will start with the topological objects. So my first, and I apologize for my handwriting in advance if you cannot read it. If you cannot read anything, please let me know. So the first thing I would like to talk about is welded knotted objects. And I will consider several families of these. So let me start with welded or W braids, which also appeared in Alex's talk yesterday. So we can think of W braids, and so the pure welded braid group on n elements as the fundamental group of the configuration space of so disjoint horizontal circles in R3. So, so we can think of this group really as so this is really something four-dimensional, so not braided tubes in 4 dimensions, but in order to understand it better, one way to think about it is as the group of flying rings. So, we have, so the base point here is just n horizontal disks. And you can think of a welded braid as a movie of these disks flying together, and then stacking these movies can give us a 4-dimensional picture. So really, this is the group of braided tubes in R4, which have only a special type of singularities called ribbon singularities. So with only ribbon singularities. And one way to picture this, again, I will just be drawing the picture in 3 dimensions. So if we have 2 tubes crossing each other, then so each of them has a filling where the singularity for one of them just cuts it completely in half, and then the other one is completely internal. So both of them are bounding disks here. These are these ribbon type of singularities. And so the braid group, as we saw again in Alex's talk, has an Artin presentation. And it, so I was talking about the pure braid group here, but in fact, the pure welded braid group, but in fact, we have the usual welded braid group as well. So just WBN. Which let me just write it here for a moment, which surjects into the symmetric group. And we have the kernel, which is the pure welded braid group. And so the welded braid group has an Artin presentation. Where I will not list all the relations, but let me just mention the generators. So we have the, so from a combinatorial perspective, we have this crossing, which you can think of as the movie of disks where one disk flies through the other and then they fly apart. And this type of crossing from the combinatorial Reidemeister perspective, where we have the 2 disks just flying and passing each other. So, so we have the story of welded braid, these higher dimensional braids, versions of the usual braids, this can be generalized to w-tangles or welded tangles. So these are, again, ribbon knotted. So we have only these special type of singularities. So ribbon knotted tubes and tori. So we're allowed closed components in R4. These again can be visualized through these movies of flying discs. In particular, these were studied, especially in work of Sato from 2000. And yet further generalization is that of W foams, where we allow some further singularities. So the collection of all W foams is again ribbon knotted tubes and tori in R4. But we allow the additional type of structure to appear. So with trivalent vertices. So from this movie, so let me just say first from the combinatorial perspective, we have this picture. From the movie perspective, these are flying discs where they merge and then they fly together. And we also have an additional structure, which are caps. These can be drawn combinatorially like this. And this is just thinking about a disk shrinking to a point. And let me mention that, so we have the topological objects, which are these ribbon knotted tubes and tori. And there is the combinatorial Reidemeister perspective on these. So, and that is only conjectural. So if we, I'm going to treat the welded tangles and welded foams as being defined from the combinatorial Reidemeister perspective. And the fact that they correspond exactly to these topological objects is only conjectural. So there's partial evidence to support that, but let me mention that this is a conjectural Reidemeister theory. Now, one way to think more algebraically about these topological objects is from the perspective of a construction on algebraic structure called a circuit algebra. So let me tell you a little bit more about that. So circuit algebras were originally defined by Barneton and Dancho in 2017. And it was specifically for the purpose of describing, finding a more natural presentation of welded and virtual knots. So they show that welded tangles and also welded foams have the structure of a circuit algebra. And let me just explain a little bit more what that means. I won't define it in full generality, but I would like to give you some idea of this algebraic structure of a circuit algebra. So what I mean by this is an algebra. So from an operatic perspective, this can be thought of as an algebra over the operad of wiring diagrams. So let me explain what kind of information this structure carries. So this is a collection of vector spaces indexed by a pair of sets. So I'm going to index them by I and J, where I and J live in some big alphabet, which I'll call curly I, some fixed alphabet. And they also have action of the two symmetric groups for each of these sets. So this is part of the information, and there's also a collection of linear maps between them. So this is where the operative wiring diagrams comes in. So there's also linear equivariant maps. Operations on these vector spaces, which are parameterized by wiring diagrams. Oops, sorry. So let me show you a picture of a wiring diagram. So one way to visualize this is a disk with holes, which are numbered. And there's some non-planar, so completely combinatorial connections between them. So here's an example. There might be also some just loose strings around. So this is an example of a wiring diagram. So this is a non-planar, completely combinatorial or perfect matching between points on the disks and the boundaries. So combinatorial connections. And another way to describe this is as perfect matchings. Oops. And so this wiring diagram would give us a map from V to 1. So here, the first component has 2 incoming and 1 outgoing piece of the strand. So this would be corresponding to some element of V21, and then V20 in the second component, and V11 in the third. And this maps to the external boundary, which corresponds to V12. So it would such a wiring diagram would produce in a circuit algebra a linear map of this form. And in fact, we found that there's an even more natural way to think about these circuit algebras from the perspective of homotopy theory. So together with Doncho and Robertson.
Eva, can you hear me?
Oh yeah, hi.
Oh, hey, it's Nancy.
Oh, hi, Nancy.
Hi. I have a question. So I'm not quite understanding how you wrote down. So I see your wiring diagram, but how am I to interpret that map on the tensor product? Is somehow the arrows giving me that information? Or?
Yeah, exactly. So the inputs are whatever these 3 disks are. So these holes in our bigger disk. And so, I'm simplifying it a little bit here because they would actually be labeled by some elements of a set, not necessarily just keeping in mind the orientation. There will be some extra information, but in particular, there's 2 incoming. So that's where the 2 comes from. And there's 1 outgoing. So that's why we're going to have V2.
So there's 3 tensor components because you have 3 sort of holes in the wiring diagram.
Exactly.
And then labels you have are how many in, comma, how many out for the arrows.
Exactly, that's right.
Okay, thanks so much.
Yeah, thanks for the question. Yeah, good to hear from the audience as well. So we have an even more natural homotopy theory perspective on these circuit algebras. So as I mentioned, they can be realized as algebras over an operad, but they're a certain even more directly operatic structure themselves. So we show with Jana Dancho and Marcy Robertson that so an abstract circuit algebra, so one can consider in fact the category of all circuit algebras with morphisms between them defined appropriately, these precisely correspond to the category of all wheeled props. So they are more general than just an operad, a wheeled prop is a generalization of a prop with the notion of a trace. So I won't go into the detail of this construction. I just want to mention there is an even more natural operatic way to interpret circuit algebras. And I hope this will have interesting implications in homotopy theory in the future. So, all right, let me also mention that this generalizes earlier work. By Von Jones, who introduced planar algebras, and they are the natural setting for usual tangles. So usual tangles are a planar algebra. And the main difference between a circuit algebra and a planar algebra is that the connections inside these diagrams defining the operations, they're not just combinatorial, connect in any which way the strings. In a planar algebra, these connections are an embedded one manifold. And so it's actually important how these strands sit in the plane, and they cannot cross in the way that these purely combinatorial ones did. So yeah, so this additional, just feature of circuit algebras is what makes them more natural for the study of virtual and welded tangles. So let me give you now the full circuit algebra presentation of welded foams. So I promise that this is the natural setting for welded foams. So they're the circuit algebra with 4 generators. So we have the 2 types of crossings. We have a trivalent vertex, and we have the cap. These are the generators that the circuit algebra has, and there's also a collection of relations and a collection of auxiliary operations. Let me mention those as well. So the relations are given by the framed Reidemeister 1 move, which is just, locally, we can replace a piece of string like this with a piece of string like this. The Reidemeister 2 move, which is telling us that 2 strings can be untwisted. The Reidemeister 3, which is saying that we can pull a string through a crossing. Oops, sorry, my crossing went the other way. And then we also have, so the more unusual relations are Reidemeister 4, which is telling us how the trivalent vertex interacts with the crossing. So if you have a trivalent vertex and a crossing above it, we're allowed to pull that underneath the vertex. So the welded structure comes from this overcrossings commute relation, which is saying how so a strand can go across a virtual crossing if the strand crosses over, hence the overcrossings commute relation. And finally, how the relation on how crossings, sorry, I'm losing my generators. I'll just move this over here. And the final relation is on how crossings interact with the cap. So the cap pull-out relation, which is telling us that if you have a cap that can be pulled through under a crossing, that can be pulled through. So as I mentioned earlier, we know that the topological objects, these knotted tubes and tori that I described, satisfy all these relations. It is still conjectural whether these are all the relations which describe the topology, or that whether there are further relations. And let me mention just briefly the auxiliary operations defining welded foams. So there are 4 types. I will only like to mention one in some more detail. So we have the orientation switch. So this is of some strand E. I'll just say the next one in words. So this is the adjoint. Oh, that's a good question. No, that's a great question. What is the topology of the tube? Yeah, so I think the best way I can describe it is visualizing this tube as a movie of flying discs. So if you put this movie together, it's these discs coming close to each other. One of them goes under the other, and then they merge, and then they keep flying together. So that's one way to visualize it as a movie. The trivalent vertex. I hope that answers the question somewhat. Sorry, that was a question in the chat. Yeah, so in fact, notice that there's going to be more than one type of trivalent vertex, depending on, from the movie perspective, how these disks, maybe one flies over and joins the other, or maybe the one on the left goes under, so there's various options. And in principle, we would need multiple trivalent vertices, but the auxiliary operations, these additional operations, allow us to only require one. And so the other ones will be obtained from this one together with the other generators and the auxiliary operation. Yeah. So, all right. So the auxiliary operations, we have the orientation switch. That was the first one. Then we have the adjoint, which switches the orientation of the strand. And whenever the strand crosses over, that crossing is conjugated by a pair of virtual crossings. It won't be important for the rest of the talk, so I will not. Yeah, I think that was, yeah, there are singularities, yeah, in these crossings create singularities. There was a question in the chat as well. All right. So, so the adjoint operation I described, there's the deletion operation, which deletes long strands. So a strand which does not connect to any of these trivalent vertices can be deleted through this operation. And finally, the most important one is the unzip operation. So this is deletion. And we also have unzip. This unzips a strand between 2 of these trivalent or phone vertices. So unzips E between 2 phone vertices. So let me draw a picture of this. So suppose we have 2 of these trivalent vertices with something interesting going on in the middle. Then this unzip operation so splits these strands and then follows the blackboard framing in the following way to create 2 strands out of 1. Okay, so maybe let me draw just an example of an element in this circuit algebra of welded foams. So we could have a wiring diagram. Suppose there's multiple connections in there with 3 disks. Suppose they connect in this way with some orientation. Oops. I need a few more details here, like this and like this. And then we can plug in generators in each of these, one of the generators. So for instance, here we could have the cap and the crossing. Let's say it's oriented this way. And for instance, here it could be a trivalent vertex. So in this way, we can generate all of the foams through circuit algebra operations and these generators. Okay, so let me mention that there's also an indexing of these objects by their skeleton. So we can define the free circuit algebra just generated by these two types of topological interesting pieces of the generators. So no crossings, but just the cap and the trivalent vertex. So this is the circuit algebra of W foam skeleton.
Hey, Eva, I have another question.
Mm-hmm.
So the trivalent vertex, does it always have to have a 2 in, 1 out orientation? Or is there sort of like the flipped version of 1 in, 2 out? Like, can two circles split apart?
Yeah, they can. I think Gigi likes to call them marriage and divorce. So yeah.
So when you're drawing the skeleton, the trivalent vertex, it's not an oriented thing.
Oh, it is. Yeah, it definitely is. So you're right. I skipped the orientation for the unzip operation, but so we could have multiple types of trivalent vertices. Either it could be 2 in, 1 out, or 1 in, 2 out. So there's two options. Either like this, or like this. So we cannot have 3 in or something like this, but this type, the 2 in, 1 out, or 1 in, 2 out is allowed.
Okay, so when you're writing down the skeleton, are we keeping track of the orientation, or like you have the cap and the trivalent vertex?
You're right. Oh yeah, sorry. I was suppressing the orientations here. You're right that in principle, everything is oriented. Yeah.
Okay, that's fine. You can leave it out if you want, but okay. But we are considering the two orientations.
Cool. Yeah, thanks for keeping me honest. I think I will keep leaving it out, but yes, there is an underlying orientation.
Well, thank
you. Yeah, sure. Thanks for the question. Right, so we have this circuit algebra of skeleton, and then there's a projection from each of these welded foam spaces. Remember, having the structure of a circuit algebra meant that we have these spaces indexed by pairs of sets. We can project to the spaces for the skeletal circuit algebra by, so the main thing this projection does is whenever it sees a crossing, it flattens it and it leaves everything else alone. And then we can define welded foams with this particular skeleton where as pi inverse of S, where S is an element of this circuit algebra. And so there's an indexing of the circuit algebra of welded foams by these the skeleton. So whatever keeping track of what is the underlying skeleton for each object. Now, okay, so keeping that in mind, let me talk about now how can we use this algebraic structure. So I'd like to talk about associated graded and homomorphic expansions. So using this structure of welded foams, there is a way to define powerful knot invariants, or universal knot invariants, or homomorphic expansions. So if we take the linear extension of welded foams, so we allow linear combinations there, this is filtered.
Can I ask you a quick question? Sorry, one more.
Yeah, of course.
So the map pi that you're doing, is this just an algebraic operation, or are you thinking about these as like knotted tubes? And so you're saying that the sort of swapping tube, you're now threading the tubes, or is it just an algebraic?
That's a good question. I think of it just in the algebraic setting as this is we have these two circuit algebras. This is a homomorphism of circuit algebras, which I think there is likely a topological interpretation as well. But for my purposes, I just think of it from the algebraic perspective. Yeah.
Okay, great. Thank you.
Yeah. So if we think about the linear extension of these welded foams, this is filtered by its augmentation ideal. Which is given by, so exactly all the linear combinations of elements, so of these welded foam elements, where the coefficients are rational numbers and such that the sum of all the coefficients is 0. So we have this filtration. And so then we can consider the associated graded with respect to this filtration, which I'm going to call A. And in fact, I'd like to consider the degree completed associated graded. So we allow infinite combinations of these quotients. And so this space also has a nice interpretation. So this is a graded space, and it can be studied combinatorially, so as arrow diagrams with a W foam skeleton. So let me just show you what some of the objects in this space, so an example of an object in this space. And I will not go through the whole set of relations, but so we have some skeleton which has trivalent vertices and caps and just long or straight strands. And then there's arrows on these components. So this is an element in here. And the set of relations has also been described explicitly by Barnatan and Dancho, coming from the relations on the original circuit algebra of welded foams. So this is also inherits the structure of a circuit algebra. Maybe let me mention one key property that this space has, which plays a key role in connecting this to further algebraic ideas and Lie theory. So if we consider all the elements in here, which live on the skeleton with just n straight lines. So I'm fixing this particular skeleton, then for that fixed skeleton, this space is a Hopf algebra. Where multiplication is defined by stacking. Just stacking of these diagrams. And co-multiplication is defined in the following way. So if you take a diagram, an arrow diagram of this type, then you sum over all the ways of splitting its connected components between the first and the second component. So it's sum over all the ways of splitting D into connected components. So for each connected component, there's a choice whether it goes in the first tensor factor or the second, and we can split it in this way. So since this is a Hopf algebra, then by the Milnor-Moore theorem, it can actually be realized as the universal enveloping algebra of its primitive elements. And the primitive elements here are exactly all the types of connected components. So as a vector space, this is just a collection of all the possible trees, as well as wheels. So maybe let me just draw a picture of what a tree would look like. So something like this. And another type of connected component could be a wheel. So it's of this form. So we could have elements like this being some types of primitives, and then this is precisely the universal enveloping algebra for that collection of elements. Okay, so now that we have the welded foams and their associated graded, let me tell you what a homomorphic expansion is. So this is now a type of not invariant, or in this case, welded foam invariant one can define. So, so this is a map from the linear extension to its associated graded, which is a filtered circuit algebra homomorphism. Which commutes with the auxiliary operations. And it satisfies a certain universality property. So namely, since taking associated graded is functorial, we can take the associated graded of this map, which now goes from A to A. And the universality property requires that this is the identity. So it's interesting to look for such a homomorphic expansion, because one, it would give us more information about this topological space of welded foams, but on the other hand, it could lead to some interesting algebraic structures on the graded side. And case in point, so another theorem of Barnetan and Dancho from 2017 tells us that considering the collection of all homomorphic expansions on welded foams, there's a correspondence or a bijection between those and certain interesting objects in Lie theory, namely the solutions to the Kashiwara-Vergne equations. So let me add an extra technical property that they have to be group-like. So group-like homomorphic expansions. As I mentioned, from welded foams to their associated graded correspond to solutions of the Kashiwara-Vergne equations. So let me tell you some more about this construction coming from Lie theory. All right, so let me say a few words first about what the Kashiwara-Vergne equations are. So the first approximation is thinking about the Baker-Campbell-Hausdorff formula, which is telling us how exponentials behave in the non-commutative setting. So if we have that x and y don't commute, suppose they're elements of a Lie algebra, for instance, then the product of their exponentials is not equal to the exponential of the sum. And the BCH formula tells us exactly how to expand this. So this is log of e to the x, e to the y. So what would be the resulting power here? And so this, the answer is an infinite Lie series. So that starts with x plus y, and then there's a half of the Lie bracket of x and y, and then some further terms. For instance, if x and y are matrices, then their bracket would just be the commutator. And the Kashiwara-Vergne equations are an upgrade or a refinement of that. So let me say a little bit of a historical background before I write them down. So this is an upgrade of, if you like, of BCH. So they were originally defined in the 70s, introduced in the 70s by Kashiwara and Vern, whose motivation was to study the multiplicativity of the Duflo isomorphism. So they wanted to prove multiplicativity. So there's an isomorphism between the center of the universal enveloping algebra of Lie algebra and the invariant part of its symmetric algebra. So they're certainly isomorphic as vector spaces, but to show that they're isomorphic as algebras, Kashiwara and Vern introduced this set of equations, or their conjecture. So this was solved in 2006 by Halacheva and Meinronken. So let me mention this. And it was reinterpreted by Halacheva-Torosian, as well as Halacheva-Enriquez-Torosian, through Drinfeld associators in 2008 and 2010. So they reinterpreted it from the perspective of Drinfeld associators. Let me just put the initials here. So Halacheva-Torosian and Halacheva-Enriquez-Torosian, so used Drinfeld associators. So, okay, so what are the equations? So if we consider the group of tangential automorphisms acting on the exponential of the degree completed Lie algebra on two elements. So V2 here is the degree completed free Lie algebra with generators x and y. And so we take the exponential of that, and tangential automorphisms we can think of as basis conjugating automorphisms on the exponentiation of the Lie algebra. So these are, I won't give the full definition, but these are basis conjugating. So they act by conjugation, automorphisms. Now, the Kashiwara-Vergne conjecture claimed that there is a solution. So they were looking for an element of this group of tangential automorphisms such that, and the first equation will look familiar from the setting of the Baker-Campbell-Hausdorff formula. So f applied to e to the x, e to the y is e to the x plus y. And there's a second equation, which is a little bit more technical. Let me just outline it. So applying a non-commutative Jacobian to f leads to a certain expression in terms of a power series. So it leads to rx plus y minus rx minus ry, where r is a power series. R of u is a power series in the variable u. where J here is a certain non-commutative Jacobian. Which is goes from tangential automorphisms to cyclic words on two elements, defined by the so a certain cocycle property that JH is equal to J of G plus G acting on J of H, as well as a certain differential property, which I will not write down for the sake of time, plus differential at zero formula. Oh. Okay, sorry. Property. Okay, so this is what the Kashiwara-Vergne equations look like. Let me explain some work with Dancho and Robertson, which further interprets these from the topological perspective. So we already have the theorem of Barnatan and Dancho, which I mentioned over here, which is saying that solutions to these equations, namely examples of tangential automorphisms which satisfy these equations are in correspondence with homomorphic expansions for welded foams. But there's also a group of symmetries which act on these solutions. So I'm going to write this space of tangential automorphisms as solutions of the Kashiwara-Vergne equation. So this is the collection of all F satisfying the two properties. Let me go ahead and explain our further work, which relates this further to the topological picture. So I'd like to talk about a topological characterization of the KV groups. So there's further information beyond this set of solutions. There's two symmetry groups acting on this space of Kashiwara-Vergne solutions called KV and KRV. So again, thinking about the filtered and graded setting. So R here relates to grading. So these two groups act freely and transitively. Let me define the graded side, which will be the one I would like to talk about a little bit more. So these are again tangential automorphisms, which satisfy the property that they fix the exponential of the sum. And again, there's a certain Jacobian condition, so that the Jacobian of this tangential automorphism is again given by some expression involving a power series. And in fact, you might object that here we don't have just the information of alpha, this tangential automorphism, we also have the information of this power series. And so one would naturally think about a pair of alpha and S. But in fact, the power series is always uniquely determined from alpha. So we don't need to specify that extra information in advance. And so the action then is, so this is a right action. So given an element in this group, oops, sorry, let me write it on the right. Acting on an element from the solution space. This is just the composition with the inverse. So it's fairly straightforward. And so one natural question that we answered is how to interpret this group topologically. So we know that the solutions correspond to the homomorphic expansions. And so how can we think about this group acting on the solutions? Well, so going back to the associated graded space of welded foams, and we can think about certain automorphisms on that space, which is, so let me just remind you, this was the associated graded of the linear extension of welded foams. So this is the group of skeleton preserving filtered circuit algebra automorphisms which commute with the auxiliary operations. Maybe I want to add that extra piece of information. So think of that as some auxiliary structure on the circuit algebra that they also have to preserve. And so the condition is, now this space, if we think of it as a circuit algebra, it has 3 generators. And so what does an element in here do to that space? So due to each of the generators, so this is one type, so this is one type of generator, an arrow on just a linear skeleton. And actually an automorphism here has to fix the arrow. And on the other interesting pieces from the skeleton, so it has to take them to some exponentials inside. So preserving the skeleton, but and then similarly, the cap has to go to an exponential. So a collection of arrow diagrams with the same skeleton, namely the cap. And so when we have an object, an automorphism here, composing with that is going to preserve the property of being a homomorphic expansion. So then G is an automorphism of A if and only if for every homomorphic expansion then the composition is also a homomorphic expansion. And so we use this property in order to relate these automorphisms to that group, Kashiwara-Vergne group acting on solutions. And in order to describe that connection, we'll first need to, in fact, take a completion of the welded foams. So we'll need the pro-unipotent completion. Which is, so I'll just write it as WF hat, which is the inverse limit of the system given by welded foams quotiented by powers of the same augmentation ideal that was used to define the associated graded earlier. And then, oh yeah, question?
Quick question, Nancy again. When you say that Z composed with G is also a homomorphic expansion, is what is there to check? So it's a filtered circuit algebra. It commutes with the auxiliary operations. Do you just have to check the universal property? Like, is that what could get messed up with that composition?
Exactly. That's right.
Okay. So you just have to check that it's graded. So once you take the composition, that the grading of that map is the identity again.
Yeah, that's right. The universal property is the thing that we still need to check. Yeah.
Okay.
Yeah, exactly.
Well, is
So
there
then-
any when one of these maps wouldn't, or like what would break that universal property? Is there like an obvious obstruction, or is that like a complicated question?
That's a good question. Can't think of one right now. Maybe let me think about it and tell you later. Yeah.
Okay, that's cool. Thanks, Eva.
Yeah, sure. I think, yeah, one of the key properties is that, well, we require these automorphisms to fix the arrow. Maybe that's one. I mean, if we didn't require this, that could be something that could break. Maybe, let me say it this way, that it fixes the single arrow, because then, in fact, the homomorphic expansion, the way each homomorphic expansion has to take the crossing to the exponential of the arrow. This is the linked to the universality property. And if we didn't necessarily require this of the automorphisms, then this might break. Maybe that's hopefully partial answer to your question. Yeah. Okay. So once we take the pro-unipotent completion, there's actually a bijection between homomorphic expansions. So there's a way to get from a homomorphic expansion isomorphism of circuit algebra maps going. So that's no longer a homomorphic expansion necessarily, but it's an isomorphism of circuit algebras. And this is what's going to allow us to go easily between the graded and the filtered side. So let me state the theorem in the remaining time. So this is joint work with Dancho and Robertson from 2001. So here is the picture. We have these maps which are giving us isomorphisms between the circuit algebras. And we have the group of automorphisms of this completed circuit algebra of welded foams, and the group of automorphisms of the associated graded. Now, these isomorphisms are in bijection with homomorphic expansions, which we know by Barnatan and Dancho are in bijection with solutions of the Kashiwara-Vergne equations. And remember that here we had the two actions of the two Kashiwara-Vergne groups, so KV and KRV. And so in our work, we show that there is in fact an isomorphism between each of these pair of groups. And so this bijection is intertwined by the two types of actions. Let me just say a couple of words of how the proof goes, just very briefly on the graded side. So the easier side to think about is the graded setting, where we can then take it back to the filtered setting using this non-canonical isomorphism just for a choice of an expansion. So on the graded setting, we have the action of the graded Kashiwara-Vergne group on solutions, which is just composing with the inverse. And we also can think of an action of these automorphisms on a homomorphic expansion, which is again exactly composing with the inverse. And now, what is the map? So we can define it from automorphisms of A to KRV, where a given automorphism, this is determined by what it does to the generators. But remember, it has to fix a single arrow. So it's determined by what it does to the trivalent vertex and to the cap. And so here we're going to get this, a pair of tangential automorphism, and I will include the information of the power series as well. But as I mentioned, that's uniquely determined from the automorphism, where roughly speaking, alpha is going to be the value of the trivalent vertex, and S is going to be the value of this generator on the cap. So the devil here is in the details, but there's a way to get a Lie theoretic interpretation of this piece of, oops, sorry, no, I meant the trivalent vertex of arrow diagrams, which are in fact isomorphic to arrow diagrams on just two strands. Remember that this can be realized as a universal enveloping algebra. And the second component lives in arrow diagrams with this vertex, which can be realized as, in fact, just a power series in a single variable. And so this is a way to obtain this isomorphism and gives us a topological interpretation of the Kashiwara-Vergne groups. Let me just say that this is connected to a similar story for the Grothendieck-Teichmuller groups acting on Drinfeld associators. So this is a classical story related to parenthesized braids and chord diagrams, which in this case are welded foams and arrow diagrams. Okay, I'll stop there. So thank you.
Yeah, we have one question. Eva, can I ask something? Not so, something naive. In the beginning, you said that there are ribbons which are braided in R4. I thought in R4 everything is unbraided.
But you have the tubes. They're not just a piece of string. It's a two-dimensional object.
So they can be still braided in R4?
Yes.
That's interesting. I'm not an expert, so it was surprising too. I thought that you can, everything can be unbraided just by adding one dimension up. Yeah.
But I think that's when you think about just pieces of string. If you're thinking about one-dimensional braids in R4, then you're right, that's trivial. But if you think about tubes, so two-dimensional tubes, you know, these surfaces can go through each other, like the way I was describing these flying rings, this movie of rings, and then you can create things which cannot be undone. Singularities, yeah.
Okay, thank you for your
Thanks.
for the answer.